Thank you. Good afternoon, everyone. Again, my name is Michael Heiber, and thank you for joining us for this next session discussing AI use cases in R&D with a special focus on materials discovery and development using materials informatics technologies. It's a somewhat stressful but also very exciting time to be in the materials and chemicals industry. It's a time of extremely rapid change and transformation in the industry. Some companies and sectors are really struggling, while others remain very profitable. Across the world, the demand for innovative materials and chemicals to help propel us into healthier, more equitable, and more sustainable future remains very strong. And there are big opportunities for new leaders to emerge with this strong vision and innovation engine. While in this session, we'll mostly talk about materials and chemical R&D, many of the AI technology trends that we discuss are similar in life sciences and high-tech manufacturing industries as well. So again, my name is Michael Heiber, and I'm the Director of Professional Services leading Enthought's Materials Informatics DX consulting practice. I come to this work with a PhD in polymer science and many years of academic research experience combining theoretical, experimental, and data-driven approaches to scientific discovery and materials engineering. I've been at Enthought for almost 6 years and have experience tackling a wide variety of industrial materials informatics challenges with our industry partners, first as a software developer or scientific software developer, and now managing teams, as well as providing higher-level strategic consulting and DX solution design services. I'm also very well connected in the global materials informatics community, and I put together today's presentation to share with you all some insights and trends that I've observed over the last few years. Today I'm going to emphasize that materials and chemical innovation, due to the adoption of machine learning and AI technologies, is accelerating, and that this is enabling a new product engineering paradigm that could present major business opportunities for both materials and chemical suppliers, as well as the firms that rely on materials innovation to differentiate their engineered products. Then I'll dive into some of the AI and materials informatics technology trends that are driving this paradigm shift. Finally, I'll summarize and then hand over the podium to my long-term collaboration partner, Mizuno-san of Idemitsu Kosan, to talk about some of the ways that they are leveraging AI to help transform their business. So let's start by talking about what is enabling the acceleration of materials and chemical innovation. Over the last decade, AI technologies have been increasingly integrated into the traditional R&D learning cycle to assist people with collecting and processing data and then making difficult decisions about how to tune the input variables to their process, such as the chemical structure, the formulation, or the processing conditions, to create materials with properties and performance metrics that are desirable for targeted applications. This trend now continues with new AI technologies able to take on more and more of the human decision-making up to the point of being able to operate completely autonomously in some cases. With these developments, we are now transitioning from a big data, fourth generation paradigm into the fifth paradigm, which is leveraging AI technologies to orchestrate many different methods. This is dramatically accelerating how fast we can collect data and learn the complex relationships, such as those between composition, processing, structure, properties, and performance. So now that we are able to learn the fundamental relationships faster, how does this change how we engineer products? Due to this acceleration, I believe we are also entering a new engineering paradigm with potentially broad-reaching impacts on many industries. In industry, innovation speed allows companies to be responsive to change in the world and adjust their products and services to meet changing requirements from customers, supply chains, regulations, and complementary technologies. Innovation speed enables organizational agility and robustness, which are extremely important in today's changing world. But this new engineering paradigm does not just offer a minor acceleration of your current processes. It allows companies to fundamentally change and improve how they deliver value to their customers in ways that helps differentiate their products, increase market share, and increase profit margins. So now let me explain how and why things are changing. To understand where we are headed, we must first look back at the last major engineering paradigm shift. In the 1980s, complex product engineering experienced a major shift from a sequential engineering approach to a concurrent engineering approach. This paradigm shift was led by Japanese automakers and also adopted by electronics companies as well. And it's one of the big reasons for Japanese global economic success starting in the 1980s. As a product of Japan's consensus-oriented decision-making culture, it almost seems natural that when making a big product design decision, you would collect all the thoughts and insights from all the different affected departments, including sales, marketing, design engineering, manufacturing, purchasing. You'll get everyone together, and you're going to talk about what to do. However, in the rest of the world, where sequential engineering was dominant at the time, this was largely not how big design decisions were made. Instead, the concept was first determined and then handed off to engineering, and then finally manufacturing would get involved much later. And when inevitably manufacturing issues occurred, it triggered design changes that would start this process over. However, Japanese leaders figured out that by getting everyone involved early in the design, they could share information and concerns that allowed them to resolve big issues faster and then divide up the remaining work to be executed in parallel. This dramatically accelerated auto design cycle time, reducing the typical time from 6 years down to 3 years. And at the time, American car companies were amazed at how fast Japanese companies could integrate market feedback and new technologies into the next model design that they released. With this accelerated learning, they could focus on the things that were most important to their brand, such as performance and quality. Concurrent engineering is now the standard practice across the globe for any kind of complicated engineered product. And as this practice has become more formalized and we've seen an increase in computational power in the 90s and 2000s, there's been adoption of other computational software tools that can further accelerate this now to down around 2 years for a typical automotive design cycle. So now let's look a little forward. If you think about the design problem, how to create an automobile, it's amazingly complex, and it requires setting thousands of input parameters to make the design. And taken all at once, it seems almost intractable. And so to make things easier, we've come up with a design engineering approach that allows us to break the problem down into subsystems and tiers. And then we have specialized teams working on the specific subproblems independently and in parallel. However, in reality, many of these subsystems are actually not independent of each other. They're related. And so to create an optimized solution for each subproblem, we're ultimately creating a solution that's a local optimization, not a global optimal solution. Even with good communication and collaboration between subteams, the results are almost always not globally optimal. The solution is constrained by the organizational structure used to create it. And we've decided to trade optimality for speed and simplicity. However, today, AI and other digital technologies are helping us tackle complexity, which allows us to make fewer simplifying assumptions and effectively seek out and find more globally optimized solutions. So if we take a deeper look at the auto design problem and how the problem is split into these subsystems and tiers that I mentioned, we can see at the bottom here, there's tier 3, and that's where the materials design more or less happens. And the problem is, while the design is happening in a 2 to 3 year design cycle at maybe the top 3 levels, the bottom level materials design is happening much, much slower. And so this is happening out of sync with the rest of the design. And because it's historically slow, the tier 2 part designers that use the materials, they don't they treat this largely as a materials selection problem. And so on the time scale that they care about, the materials available to them are largely fixed. And so they're simply selecting from a variety of material types as well as grades which one would be best for their particular part or assembly that they're working on. And so they're looking for specific materials properties that will help them design their part. To them, again, because the design cycle is so slow, there are very few degrees of freedom when it comes to materials used inside of their design. For example, a car bumper, the design team is only selecting from a few metallic alloys, plastics, and grades within those. And these options typically don't change a lot from year to year. However, today, AI is rapidly accelerating the pace of materials development, which allows materials design now to occur on a similar timescale with the rest of the design in the system. This opens up exciting new possibilities and represents a new paradigm called concurrent materials design. In this new paradigm, Tier 3 suppliers can create AI models that accurately predict the complex multifunctional properties of their products as a function of the composition, processing parameters, and others, and then provide this information and capability to their customers in the form of a recommended materials design space. The Tier 3 supplier now has created a value-added product that includes data-driven engineering services in addition to the final materials sold. With this service, Tier 2 part designers can then access many more degrees of freedom in the materials design space that was previously unavailable to them. And they can use that to co-optimize the materials composition, the processing, the part design, and cost to create a much better product and solution than they could have before. What I'm describing to you is not a fantasy. This is how truly superior products are made today. Leading American and European companies are already pursuing concurrent materials engineering and design, with a variety of publicly announced activities by companies like Dow, Covestro, 3M, Apple, SpaceX, and Tesla. I can refer back to SpaceX that we heard from Brian earlier. This is something that they're very keen on as part of their fail fast mentality, is not just, again, changing the part, but also changing and optimizing the material that's used to make that. So they also have experts in metallurgy, alloy design, processing, and all involved with the systems level engineers designing the ultimate rocket. And privately, there are many more other initiatives like this currently happening out in the world that we just don't know about. So today, we are on the cusp of this paradigm change. Japanese industry was a leader of the last major engineering paradigm shift to their great benefit, and they can be leaders again with effective leadership and decisive action. So now let's take a look at some of the major AI and materials informatics technology trends that are driving this concurrent materials design engineering paradigm forward. In the academic world, while data science has been a hot topic for 10 to 15 years now, its application to materials and chemical R&D problems has really only emerged over the last 5 years at a large scale. So I've plotted here the number of publications that use AI machine learning to develop new insights into materials and chemistry as a function of time. And you can see the last 2 to 3 years has seen an explosion of activity catalyzed largely by the development and use of more specialized data science tools that are specifically optimized for material science and chemistry problems. And this trend continues to this day. Literally every week, there are new and improved open source technologies and tools released that make complex materials discovery, development, and design problems easier and faster. There are bigger and better open data sets for training models and testing algorithms. There are foundation machine learning models for atomic potentials that are accelerating ab initio simulations. There are machine learning model architectures optimized for property prediction. There are new ways of embedding known physical relationships into machine learning models so that you can increase the accuracy of the model with less data. There are new specialized multi-objective optimization algorithms better suited to the realities of experimental science. And there are generative models to prompt humans to try unexplored areas of their design space and even discover completely new materials. And finally, there are also new specialized large language models, agents, and agentic AI systems helping accelerate innovation. I don't have time to talk about all of these categories, but I want today to focus on the last three, which I think are particularly important. And if you have questions about the others, please feel free to find me and talk with me after the talks are done. So first, I want to emphasize the importance and developments in the field of AI-driven optimization. Pretty much all industrial materials problems are ultimately complex, multi-objective optimization problems. And teams are trying to achieve numerous challenging customer requirements under complex constraints with limited time and expense budget. And while Bayesian optimization and other adaptive experimental design methods certainly are not new, there continue to be significant advancements in making these techniques to work better on real experimental development problems. Historically, there have been challenges in making algorithms fast enough for high-dimensional optimization problems, and it can be hard to define and enforce the complex constraints due to chemistry rules, process restrictions, and IP requirements. Materials optimization problems also have dimensions that are non-continuous, such as chemical structure. Experiments are also often done asynchronously and in batches, not one at a time. And the results of these experiments can often have significant measurement uncertainty, which can confuse algorithms not developed to handle noisy data. Most product optimization is also not done in a single loop. There are many different stages of subloops and decisions made using partial information and lower accuracy estimates. The academic and open source research community have been actively tackling these issues over the last few years and keep coming out with new and improved algorithms. I've listed a few of the ones on the right, but it's important to emphasize this is a continuously evolving area that can have a big impact on how quickly teams can tune existing products to meet changing customer requirements or pursue more novel products for future. Moving on, as some of these teams are pursuing novel products, there's been a lot of work to explore new neural network architectures and genetic algorithms to create generative AI tools, not for generating text or images, but for generating new crystal structures or molecules. Some, like CGSNet, shown in the bottom right figure, can even create novel molecules with desirable properties. In this example, you can see that even though the model was trained on the QM9 dataset, that distribution is shown in the yellow. This has an isotropic polarizability property distribution shown there. When the user requests new molecules that have significantly higher or lower polarizability, the model is able to generate valid molecules that are completely new to the model and are confirmed through subsequent simulations to have polarizability values very close to the targeted value. This area is also under active development. We've now created maybe thousands of new molecules. Then we need to figure out, how do I figure out which ones I should try to make in the lab? Which ones are most likely to be synthesizable or of interest or patentable by my company? There's also challenges in doing this in areas where there's less data. QM9 is a very large data set. For some of the properties you care about, there's not an existing large open source data set to do this. And so can you do similar things with much less data on more specialized properties? These are areas of active research that continue to evolve today. And last, we come to the specialized large language models that continue to rapidly improve and are being tuned and applied in new ways, specifically for materials and chemical R&D. We've been researching these use cases for the last 2 years and have found the most mature and common use cases largely fit into 3 categories: knowledge extraction and summarization, lab assistance and agentic AI, and finally, predictive chemistry. So first, knowledge extraction and summarization is by far the strongest use case currently. LLMs are designed and optimized to mimic human language, and so perform very well on language-based tasks. Several studies and tools have demonstrated how to connect multiple steps to extract important information from documents and summarize information in a new document and present that to a user. Recent improvements in the best tools now also have the ability to include links to original supporting documents so that you can dig deeper and validate the conclusions made and maybe read further about more specific information inside of that document. For general chemistry questions and problems, the best LLMs now perform about as good as a typical master's level chemist on sort of language-based chemistry questions. With fine-tuning and RAG systems, LLMs can operate with even more specialized knowledge about your business's chemistry, about your patent literature, about your chemistry that you care about. But they still often struggle with logic and math-intensive problems. This brings us to the next use case. I just mentioned that LLMs struggle with mathematic-intensive questions. So when a task requires a lot of calculations or simulations or other more specialized operations, these can be handled separately by an agent. And an LLM system can be designed that know when and how to use more specialized agents when appropriate, and then parse out the information created by those agents to create a final response that is understandable by the researchers. These agentic AI systems can be designed and optimized to execute a wide variety of tasks, sometimes even completely autonomously, with a natural language interface that is easy for novice researchers to use. These systems can make it easy for less specialized researchers to access and use more advanced tools as needed to seek answers to their problems. And finally, there's the predictive chemistry use case. The goal here is to use LLM's ability to leverage its base training as a foundation model and only a few examples of new problems or new examples of data and quickly learn the patterns in those examples and make good predictions. It already does this really well with language, but there's also been work trying to adapt this for making numerical predictions, and not just language predictions. While there are great machine learning models, more traditional deep learning models for making property predictions with a large amount of data, the idea is that LLMs could potentially be used to learn the language of chemistry and make reasonably accurate predictions, even with very, very little data. This is the least developed use case of the three I'm showing here, but there's been a lot of recent developments in progress that's worth keeping an eye on and considering testing it out, especially on low data problems that you might have. As you collect more data, in the current status, you would probably eventually shift to a more specialized deep learning model instead. But this could bridge a gap that currently exists in some problems. So with that, I'm out of time, and I'll leave you with my concluding thoughts. We are in an exciting time in industrial materials and chemical R&D. AI technologies are dramatically accelerating innovation in ways that can have a major impact on how engineered products are designed. Concurrent materials design offers big opportunities for both material suppliers and part designers that can leverage AI in the right ways. Japanese industry was once an innovation leader in the world, but has begun to stagnate due to slow digitization, risk aversion, and a lack of agility. With the rise of AI and the concurrent materials design paradigm, there is an opportunity to leverage existing strengths, take action, and lead once again. So thank you, and I will now hand off the stage to